In this last video of topic 2, we're going to look at Taylor expansions of functions in power series. This builds on the material covered in the previous videos. You're probably already familiar with Taylor series, so some of this might be revision, but we'll revisit this concept later by developing such expansions for complex functions. To recap what we covered in the previous video, we looked at Cauchy's criterion and partial sums and how they can be used together to test for convergence. We looked at the difference between absolute and conditional convergence for a series. We looked at how to apply the ratio test for convergence. And finally, we looked at geometric series, its convergence and its limit. These are the intended learning outcomes for this video. After watching this video, you should be able to Taylor expand a real function as a power series, and you should be able to use the ratio test to find the interval of convergence for that power series. After finishing this video, I encourage you to attempt the questions in problem sheet 2, and this will help test your understanding of the material from all of the videos in this topic. Let's begin.
We're going to begin by talking about real power series. Now, a power series is an infinite sum of terms in powers of some argument x. So we can write a real power series has the form, and we denote it as p of the real argument x is the sum from n equals 0 to infinity of some real coefficients an times x to the n. So we understand this as meaning a0 plus a1x plus a2x squared, and so on. So an here are real coefficients. Now, typically we want to use power series as an approximation for something like a function. Now, if we want to use power series to approximate a function, so to approximate in this case a real function, it's important that the series converges. In other words, as we take more and more terms in this series, our approximation to the function gets ever more precise. From the previous video, we know that a convenient test for convergence is the ratio test. So we can apply that here. So apply the ratio test. The ratio test tells us to take the limit, as n tends to infinity, of the ratio of the n plus 1th and the nth terms in our series. In this case, the n plus 1th term is given by a n plus 1 times x to the n plus 1, and we divide that by the nth term. We can take out the absolute value of x out the front, and we have the limit as n tends to infinity of the ratio of these coefficients. Now, the ratio test tells us that this quantity must be less than 1 for the series to converge. It's obvious here that because the absolute value of x appears in the expression, the convergence of our power series p of x depends on the value of x. And as before, we can say that the range of values of x for which this expression holds, this gives us the interval of convergence for the power series. we will see that when we generalize to complex power series, where the argument and the coefficients can be complex, this kind of treatment will give us a radius of convergence in the complex plane. In other words, the region of convergence is described by a disk. We're now going to talk about Taylor series of a real function. We'll later talk about Taylor series for complex functions. Now, a Taylor expansion provides a way of expressing a function as an infinite power series. So let's consider some real function f of x that we want to express as a power series. And for this power series, we're going to say that the argument is x minus some fixed value x naught. And this corresponds to taking a Taylor expansion about the point x naught. So how do we go about this? Well, let's first assume that we can write f as a power series. So let's assume that we can write f of x is the sum of an infinite number of terms given by some coefficient and then powers of x minus x naught. And we can write this out as a naught plus a1 lots of x minus x naught plus a2 lots of x minus x naught squared, and so on. Now we're going to make an important assumption here. We're now going to assume that f has derivatives of every order The next task is to find the coefficients an. So we want to find the coefficients an. So taking our expression above, f of x is the sum between n equals 0 to infinity of coefficients times powers of x minus x naught. Let's first consider what happens if we set x equal to x naught in this expression. Well, the left-hand side is going to be the function evaluated at x naught, and the right-hand side, in our expansion over here, we can see that only the a0 term is going to survive. All the other terms are multiplied by x minus x naught, and when we set x equal to x naught, these are all 0. So this means that our function evaluated at the point x naught simply returns the coefficient a naught. Next, let's take the derivative of the function and its power series. So next we'll take the derivative of f of x and of its power series. So this is the line that I've marked with an asterisk. The left-hand side is going to give us the first derivative of f. The right-hand side, the term a0 is a constant, so its derivative is 0. The term after that, a1 times x minus x naught, is going to give us the coefficient a1 on differentiation. And then continuing, we'll get 2 times a2 lots of x minus x naught, and we get 3 a3 lots of x minus x naught squared, and so on. As before, we then consider what happens if we set x equal to x naught, and this gives us that the first derivative of the function evaluated at x naught is the coefficient a1. Let's repeat this procedure once more. You can probably see what's going on now. If we take the derivative again, the left-hand side is going to be the second derivative of the function f evaluated at some point x. Now, looking at this line here, the first term on the right-hand side, a1, its derivative is 0 because it's a constant. The term after that is going to give us 2a2. The next term is going to give us 3 times 2 times a3 x minus x naught. And the term after that is going to give us 4 times 3 times a4 x minus x naught squared, and so on. Once again, we set x equal to x naught, and we have that the second derivative evaluated at x naught is simply 2 times the coefficient a2. Now, it's not hard to see that if we repeat this procedure, we find that the coefficient an is given by the nth derivative of the function evaluated at the point x naught divided by n factorial, where the factor n factorial comes from the coefficients that we bring down from x minus x naught on differentiating. And with that, we're done. We found an expression for the coefficients an. Hence, provided such a representation exists, the Taylor series for the real function f about a point x naught, is, we can therefore write f of x is an infinite sum of terms whose coefficients are given by this times powers of x minus x naught to the n. And again, this is really important, so I'm going to put a red box around it. This is a Taylor series. There's a last bit of important terminology attached with this idea of expressing a function as a Taylor series. We say that a real function is analytic at the point x naught if its Taylor series, in other words, the power series given by the expression in this red box. So a real function is analytic at x naught if its Taylor series at any point x naught converges to the function in some neighborhood of the point x naught. In other words, if we consider a point in some small region about the point x naught, we can approximate the function value there by using the Taylor series expansion at x0. Now, importantly, we saw that the existence of a Taylor series requires the existence of all derivatives. And that's clear from the expression in the red box. It's important that the Taylor series converges in some neighborhood. It's not sufficient for the series to converge at an isolated point. And we're not going to encounter any examples of these, but there are functions whose derivatives are defined at the point x0, but the resulting Taylor series has zero interval of convergence, and such functions are not analytic. The last point I want to make about Taylor series and the definition of analyticity is that we will later extend this definition to complex functions of a complex variable. Now, to end this video and this topic, I'm just going to give a famous example of the Taylor series expansion of a real function. So the example we're going to look at is the exponential function. And we want to expand this in a Taylor series about the point x0 is 0. Okay, so from the red box at the top of the page, we know that we need to calculate the derivatives of f of x. And that's particularly easy for the exponential function. We know that the first derivative is e to the x, and in fact, the nth derivative is simply the function itself, e to the x. So looking at the expression at the top of the page for a Taylor series, we know that the nth derivative evaluated at the point 0, these are all going to be 1. Therefore, the Taylor series looks like this. It's the sum from n equals 0 to infinity of 1 over n factorial, and then x minus 0 is just x to the n. And this is our Taylor expansion of the exponential function about the point 0. We can apply the ratio test to find the interval of convergence. So the interval of convergence, the ratio test tells us to take the limit as n tends to infinity of the n plus 1th term over the nth term. And this will have x to the n plus 1 over x to the n. This gives us the limit of an plus 1 over an times the absolute value of x. And we know that this has to be less than 1 for convergence. We know that the nth coefficient is given by 1 over n factorial. So this expression here gives us the limit as n tends to infinity of n factorial over n plus 1 factorial. So this implies that this holds. Now n factorial divided by n plus 1 factorial is just 1 over n plus 1. We can take this limit onto the other side, so we now have that the absolute value of x is less than the limit n tends to infinity of n plus 1. And this obviously tends to infinity as n tends to infinity. Hence we have that the range of values x for which the series converges approaches infinity, therefore converges for all x. So the exponential function's Taylor series expansion has an infinite interval of convergence. I'll just note that on Blackboard, on the page for this week, there's some additional content that shows you what a finite interval of convergence looks like. Interval of convergence looks like. That's the end of this video, this last video of topic 2, real analysis. To recap, we looked at power series, which is an infinite sum of terms in powers of x, and we saw that the range of x values for which a power series converges depends on the value of x. We then saw how the Taylor expansion at a point provides a power series representation for a function, and we defined what it means for a real function to be analytic. Now you'll get lots of practice in the problem sheet of all that we've covered in topic 2. Thanks for listening.